All right, welcome back. Um, so today, kind of continuing with inductors, we left off last time on inductors. We're now going to get to transformers, which I'll go ahead and foreshadow is kind of like having two inductors next to each other. Okay, now the schematic symbol that we'll be using looks like this. We have one coil, we have a separation, and then we have another coil on the other side. Okay, so this kind of does look like two inductors. And if you remember from the different schematic symbols we had for all the different types of inductors we have access to, if you notice, the core is also represented here. And in this case, solid line. And so we have these two inductors, but they're not electrically connected to each other. But we'll see. They do have a connection to each other, but it's only with a magnetic field. Now, it's probably a little easier to understand if we go over the physical transformer and see kind of what that looks like. Now, if you remember, an inductor is nothing more than a coil of wire. So what we have here is a core, some type of ferrous or ferromagnetic material, something that can concentrate magnetic fields but does not carry electrical current by itself. So we don't have an electrical connection between the core and these two coils. Now, these two coils, we're going to go ahead and give them a name. The one that we put on the left, that's going to be considered the primary windings. And by windings, we just mean wraps of wire. So quite literally, this is just wire that's been wrapped around a square core. Same thing over here, we have the secondary windings. And the secondary windings is the same thing, just wire that has been wrapped around the core. But there's no electrical connection from one coil to the other. But like I said, they will interact with each other via changing magnetic fields. Okay, so now hopefully the schematic symbol sort of makes sense. We have these two inductors that are coupled to each other magnetically, but not with a direct connection of a wire from one to the other. So they can only interact via magnetic fields. Now, this process of one winding affecting the other winding is called mutual inductance. So what's going to happen is an AC voltage will cause a changing magnetic field, and that magnetic field will in turn cause an AC voltage and AC current on the secondary windings. So actually, let me go ahead and redraw this. So I'll give ourselves, and I'll use the physical representation. So we have some core of ferromagnetic material, and we have one set of windings on one side, and another side we have the secondary. Okay, primary and secondary. And what's going to happen is we're going to apply an AC voltage. To the primary side. Now, this is going to cause an alternating current here. Now, keep in mind what this AC voltage is representing. Half of the time we're going to be positive, half of the time we're going to be negative. So during the positive alternation, you can think of your magnetic field as moving in one direction, and then when the polarity gets flipped and we go negative, now the magnetic field is going to be moving in the opposite direction. Now, these magnetic fields will also cause a changing magnetic field in this coil by that process of mutual inductance. And so the changing magnetic field that we're creating here with this coil is going to induce a changing AC voltage in our secondary. It's much like a generator. If you think about it in a generator, I hope this analogy kind of makes sense. I'm just going to draw a bar magnet here, north and south. And say we go ahead and rotate this, and then we put a coil over here. And as this magnetic field is rotating, it's causing current to move through these wires. The same thing is happening over here, except instead of a bar magnet creating the changing magnetic field, we're actually causing that changing magnetic field, we're creating it by virtue of applying an AC voltage to a coil of wire. Okay? If we just applied DC, we would not have a changing magnetic field. We would just have a magnetic field in one direction. And so we actually wouldn't get any current coming out of this side. But since it's a changing magnetic field, we're essentially wiggling the electrons left and right, and so we're going to get a changing voltage on the secondary windings. So that's kind of this idea of a transformer. So let me go ahead and also mention something else about this. I'll use the schematic symbol now. So if we apply an AC voltage to the primary, we get an AC voltage on the output, but not DC. So if I were to just apply a DC voltage, a constant applied voltage to the primary, we would actually get 0 volts on the output. We would get no voltage. Okay? So the first thing that you can think of that this transformer is going to do is going to allow AC to get through it, but not allow DC to get through it. So that's kind of the first function of a transformer, and a pretty important one. DC just can't get through it, but AC's got no problem. So you can actually think of a transformer as filtering out all DC. No DC is allowed to pass. Okay, so that's kind of our first feature. Transformers only allow AC to pass. In other words, we get 0 volts or no voltage induced on the output of the secondary if we apply DC to the primary. It's got to be AC. Okay? So that's our first feature. The next thing that we want to talk about in regards to a transformer is this idea of the turns ratio. Okay? So as I mentioned, a bunch of wraps of wire, and I got a bunch of wraps of wire on the secondary. But now the question is, how many wraps of wire do I have on the primary, and how many wraps of wire on the secondary? Or we call those turns. how many turns of wire, how many loops have we wrapped around this core on the primary versus how many wraps or how many turns of wire we have on the secondary. Okay, so we'll go ahead and define that as N sub P and N sub S. N sub P is the number of turns on the primary, and N sub S is the number of turns of wire on the secondary. So the turns ratio is the ratio of these, right? So if I had 10 turns over here and I had 10 turns over here, the turns ratio would actually be equal to, well, 10 over 10, which is just 1, but we specify that as 1:1. Okay, that's how we specify the turns ratio. So when you see a transformer, they're going to have to tell you what the turns ratio is. So this is exactly as you would see it on a proper schematic for some circuit. If we had the same number on the primary as on the secondary, we would call that a 1:1. A 1:1 transformer, meaning we have the same number on the secondary as we do on the primary. Now, the reason we care about this is because that turns ratio is going to tell us how much the voltage changes on the output. Okay, so we can actually increase an AC voltage or we can decrease an AC voltage. If we apply 100 volts over here, we could make that larger. We could turn 100 volts into 1,000 volts, or turn 100 volts into 200 volts, or we can actually make it lower. We can take 100 volts on the primary and turn that into 50 volts on the secondary, or 20 volts on the secondary. And the only thing that causes that is how many turns of wire we have on the primary versus the secondary. Okay, so that turns ratio tells us how we are going to affect the voltage. Namely, is it going to increase or decrease? So, for example, over here, I have a transformer, and on the primary, I have 300 turns. So I've wrapped 300 times, 300 turns of wire. And on the secondary, I have half as many. I have 150 turns. Okay, so half as many on the secondary as the primary. Now, when you look at the turns ratio, we come up with that ratio. 300 divided by 150 turns into a 2:1 transformer. So if I was looking at this on a schematic, that's exactly how it would look like. They're just going to give you the turns ratio. I don't care if I have 2,000 turns over here and 1,000 turns over here, or if I have 100 turns over here and 100 turns and 50 turns over here. Half as many. I hope I got that first one right. If I had 1,000 turns over here, I would have half as many turns over here, so I would have 500 turns. Okay, so 2:1. This is what they're going to give you on a schematic. Now, as it turns out, the ratio of voltage between the primary and the secondary can be calculated from this turns ratio. So, one way to put this, I could list the number of turns on the primary over the number of turns of the secondary, and that would be equal to the voltage on the primary divided by the voltage on the secondary. But you can also think of it as stepping up or down the voltage. by that factor. Okay, so in other words, with this example up here, if I put 100 volts here, I'm going to get half that voltage on the output. So if I put 100 volts here, I'm going to get 50 volts out. I'm going to get half of the voltage. For our example, I had 300 turns on the primary, 150 turns on the secondary, and this turns ratio is equal to the voltage ratio. So if I apply 200 volts AC on the primary, I'm going to get 120 volts AC out of the secondary. Okay, that's what I get from this 300 to 150 turns, or 2-to-1 transformer. Okay, if I apply 120 volts to the primary, I'm going to get half of that out from the secondary. I'm going to get 60 volts. Okay, so I'm always dividing by 2. I'm always getting half, and that's because my turns ratio is a 2-to-1. Now, when we do that, in this case, when we make the voltage on the secondary less than the primary, we have a step-down transformer. In other words, I am stepping the voltage down. I am making it less than what we're applying on the primary. So the name of this transformer would be a step-down transformer, and that's exactly what people call it, and that's what you would find in the literature. If the voltage is decreasing on the secondary, we call it a step-down transformer. We're stepping the voltage down. But what about if I want to step the voltage up? Well, all I have to do is make the number of turns on the secondary higher than the primary. So in this example, I have a step-up transformer. Because I have 20 turns on the primary, 80 turns on the secondary, I get a turns ratio of 1-to-4. I have 4 times the number of turns on the secondary than I do on the primary. So in other words, now I'm going to be multiplying whatever I apply on the primary by a factor of 4. So if I apply 120 volts AC to the primary, I get 480 volts AC on the secondary. Okay, so we call this a step-up transformer. Now, what's the difference between a step-up and a step-down that has the same turns ratio? Well, really no difference. It's just a frame of reference where I'm applying that primary voltage. So I could take the same step-up transformer, I could turn it around and get a 4-to-1 and if I applied 12 volts over here, I would actually get a quarter of that. So I would get 3 volts on the output. Okay, but that same transformer, and I should say in this case we would have a step down, but that same transformer, as we saw previously, if I turned it around, I would have a step up. So if I applied 12 volts, I would get 48 volts on the output. Okay? So the step down and step up is all in reference to what is being done to our voltage. Are we increasing it or decreasing it? Or which side has more turns? Is it the primary side or the secondary side? Now, this is actually incredibly useful because, as I've mentioned before, it is much easier to transmit AC voltage. That's why we transmit AC voltage across our power lines. It also is more efficient to have a very large voltage being transmitted on those power lines. So, when we get to our house, we are getting 120 volts RMS out of that outlet. Now, let's just say I throw in a 10 to 1. Okay, I have a 10 to 1. I have 10 times as many turns on the primary as the secondary. This is a step down transformer, and so I'm going to get 1/10 of the voltage that's being applied to the primary. So in this case, V sub S should be equal to 12 volts. Now, remember, there are 3 different ways we can talk about this voltage. We can specify it as a root mean square. We could specify it as a peak voltage. And we could specify it as a peak to peak voltage. Whatever units that I use to represent the same voltage, I need to keep that consistent when I'm talking about the voltage on the secondary. So if I have 120 volts RMS and I divide that by 10, because I have a 10 to 1 step down transformer, I have to make sure that I keep those units the same. Or it is 17 volts peak, or 34 volts peak to peak. Okay? So make sure you remember and go back to that lecture for how to convert between RMS and peak voltage and peak to peak voltage. Know how to convert those 3. A common type of question that I would ask on an exam would be something like this. And you'll definitely see this in a future exam, whether that was midterm 2 or a final. In this case, this is our final. So let's just say I give ourselves 10 volts peak. I may ask the question, looking for an answer in RMS. Now in this case, I would have to give you the turns ratio. So let's just say I have a 1 to 2. Okay, so I have a step-up transformer right here. 1 to 2. More turns on the secondary than the primary. So I'm stepping up my voltage by a factor of 2. My 10 volts peak, therefore, turns into 20 volts peak. However, I'm asking the question for RMS. So you also need to remember how to convert back and forth between RMS and peak voltage. How do I do that? Well, remember, it's VRMS is equal to V peak times 1 over root 2. 1 over root 2 is about 0.707. So let's go ahead and just do this calculation here to convert we should get 14.14 volts. So this would be the final answer for this question, because I asked it in terms of root mean square. Similarly, let's do another example here. Let's say I have 30 volts RMS applied, and the other bit of information I'll give is that on the secondary, we get 60 volts peak. Notice these units aren't the same. And I may ask, what is the turns ratio? That's a great question, right? I have two different units. I've only given you the voltage applied to the primary and the voltage coming out of the secondary. And now I'm asking for the turns ratio. Well, before I say anything about what this transformer is doing, let alone what the turns ratio is, I need to get these units in the same page, right? I need to get these units the same. So I can convert the 60 volts peak into RMS, or I can convert the RMS into a peak voltage. I'm going to go ahead and just turn the 30 volts RMS into a peak voltage. Okay, so I'm going to actually, that is incorrect, isn't it? I have to divide by 0.707. Remember, the peak voltage is higher than the RMS. So let's go ahead and convert that RMS into peak. 30 divided by 0.707, or 30 volts divided by 1 over root 2. That'll give you the same exact answer. It looks like our peak voltage is 42, and I'll take this to 2 decimal points, 43 volts peak. Now, what is the turns ratio? Well, I have both of these in the same units, but let's first answer, is this a step up or a step down? Well, look what's happening in my voltage. 42.43 peak volts is getting turned into 60 volts peak. So our voltage is getting multiplied by some number. It's increasing. So this is definitely a step-up transformer. Now, how do we go ahead and figure out the turns ratio? Well, we can go ahead and divide the voltage on the secondary divided by the voltage on the primary and figure out by what factor is this getting multiplied. Okay, so I can take my 60 divided by 42.43, and I get 1.414. So I know that my secondary must have more turns than my primary. Why do I know that? Because I'm getting a higher voltage output from my secondary. So my secondary must have the higher number by a factor of 1.414. So to answer what is the turns ratio, there it is. It's a 1 to 1.414. Okay, so these are perfect examples of questions that you would encounter on a future exam of mine. Now, let me kind of go back a little bit to overview of the usefulness of these things. What comes out of our wall is 120 volts RMS. And if you think about something that needs power, let's just say my laptop, let's say some sort of electronic circuit, 120 volts RMS is pretty high up there. So typically the first thing you do when you're creating a power supply for a device is we need to get this voltage lower. So that's exactly what we're doing here with a 10 to 1. Now this turns the voltage on the secondary into 17 volts peak. But keep in mind the transformer only permits AC voltage to drop through. So we have a high AC voltage on that primary and now a much smaller AC voltage on the output from the secondary. But let's think about the usefulness of this in regards to something like a digital device, say a laptop. I'll put a little keyboard on there and a screen. Does my laptop run off of AC voltage? No, it doesn't. All of our digital devices, all of our microcontrollers, all of our FPGA boards, every single thing you're ever going to work with as a computer engineer is 99.9% of the time going to be DC. All of our circuitry works off of DC. So we need to also convert this AC to DC. So how do we go ahead and accomplish that? Well, a few lectures ago, I showed you a circuit that uses a diode. Now, with a diode in here, We now change this AC voltage into, and if we plot RL, so in black we have V sub S, in red is going to be V sub RL, and I agree that this is not quite DC yet. This would be DC. But at the very least, we've done our first step. We've gotten rid of the negative portion of our AC waveform. We've gotten rid of all negative voltage. And it is all positive. So we can later turn this into this, but we have to do some sort of diode circuit in order to clip the negative portion of this waveform. Okay? So in a previous lecture, I showed this exact same circuit. The only difference was I used an AC voltage source over here in place of the output from the secondary. But this is really the beginnings of all of our power supply circuits. Now that's a topic for 311, but I just wanted to show the usefulness of our transformers and bring back our old friend the diode from a previous lecture and show that once we start putting all of these components together, we can really do some amazing things and some very useful, very practical circuits that form the basis of all of our modern circuitry. Okay? As far as your time spent in prepping for an exam, definitely review these two transformer problems that I went over. You have a walkthrough of me doing it. I told you exactly what I'm going to be looking for, and you can go ahead and put in your own test values and make up more of your own problems to practice. Okay? So that's all we're going to talk about in transformers, and at least for now, and that's all we really need to keep going. Okay? So make sure you know how to convert that peak to peak, and RMS voltage. Make sure you understand the difference between a step down, step up. Make sure you can calculate what the turns ratio is. If I give a turns ratio and an applied voltage, what voltage would I get on the secondary? If I gave two voltages, what turns ratio would that transformer be? Another thing I could do was this type of problem, only give the voltage on the secondary and the turns ratio and ask you for the voltage on the primary. So there's a lot of different options in how I can phrase these questions, but that would be all that you would encounter in regards to transformers. Okay? So I'm going to leave this here, and take care, everyone.